In this video, I want to talk about what linear transformations do to graphs of equations. Everything I present will be in R2, but what I talk about here will very naturally translate to R3 or even to higher dimensions than that if we wanted to look at that. For the most part, we'll focus on R2 and R3 because when we're talking about graphs, we're thinking of visualizing three-dimensional or two-dimensional space, and it's not necessarily as useful to do that in higher dimensions where visualizations are less useful. So to start into this, I want to remind you of something that you learned probably a long time ago, depending on when you took Algebra 2 or college algebra, which is how to move graphs around and stretch and squish graphs. So here's a classic example. We have the unit circle, and let's pull up the iPad as well. So yeah, so the unit circle has equation x squared plus y squared equals 1. And I want to know, what do I have to do to this equation to get this other circle, this blue one, which same radius. It was crazy. I don't know why it's so bad. Sometimes you just can't get exactly what you want. That's good enough. It's got the same radius, radius 1, but it's centered at 2, 3 instead of 0, 0. All right, so this is a classic question, and when you present this in a college algebra class, if someone hasn't seen this before, they're probably going to come up with a wrong guess that is a reasonable guess and actually really useful because you can quickly figure out why you're wrong, hopefully, of this. Now, this is not the equation of this circle. I was trying to zoom. Let's zoom back out. I don't know why the zoom is struggling today. This is the equation of this circle in red. Right? So by adding 2 and 3 to each x and y value, I moved it the wrong way. And you can then maybe come up with the correct guess, saying, well, if that was wrong, maybe I'm supposed to subtract. And that's the correct guess. Right? So the blue circle has this equation, x minus 2 squared plus y minus 3 squared equals 1. And the idea here is that this guess was reasonable, saying, hey, look, I'm trying to move all my x values right 2 and move all my y values to the right 3, but that's actually backwards. What you want is you want this equation to be true, and so you want to plug in some x value, or whatever you want to plug in for x, you want to change it so that it'll go back to what it was here. And similarly, whatever you plug in for y, you need to do something to change it back to the y value that will make this equation true. So you're not actually trying to move from this equation here, you're trying to move the other direction. You're trying to move backwards. And so that's why you have to subtract 2 and 3 rather than add 2 and 3. Right? If I plug in 1, 0 to this equation, that's correct. But to plug in 1, 0 here, I have to plug in 3 and 3, which is a point on this circle. Okay, so that's what you hopefully learned at some point in college algebra or algebra 2. How does this apply to linear transformations? Well, at risk of crazy zoom issues, let's go to about this. Remember, we talked earlier, we had this linear transformation we were looking at that took this unit circle and sent it to this ellipse in purple. And we demonstrated this by saying, look, what we're really doing here is we're starting with the unit circle and our standard basis of R2, and we're taking this green vector, and where instead of 1, 0, it's now going to 2, 2. We're moving this kind of up and to the right. We're stretching space. And we said what the end effect of that is, we leave the blue in place, is that we take this unit circle and we send it to this ellipse. And my question is, what is the equation of the ellipse? And in order to figure this out, I think it's relatively clear that we should figure out what this linear transformation is. So what linear transformation have we just applied, right? We should start with that and see how can we use this transformation to figure out the equation of the ellipse. So our transformation is t equals AV. What's A? Well, we saw that it took the first standard basis vector, 1, 0 to 2, 2, and it took the second standard basis vector, 0, 1 to itself, 0, 1. So this is the matrix of the linear transformation. And a reasonable but wrong guess at the equation of the ellipse. So let's flip for a second to just the iPad. Is to do the following, is to say, look, if we take our matrix A and multiply it by any vector x, y, and I like to write it like this, or let's just write it normal, I guess. We get 2x up here, and down here we get 2x plus y. And so I'm going to replace x with 2x. And I'm going to replace y with 2x plus y. And I'm going to see what happens. This is a very analogous guess to what I talked about with the circles example. It's totally reasonable, but it's not going to work. So what happens if we go with that? So we'll just look at the picture. That will give us, let's remove the basis vectors for a second. That'll actually give us this green ellipse. I just graphed it in here. So it's wrong. And it's a little harder to see why it's wrong in this example, right? With the circles, it was really clear that we had just moved the circle in the wrong direction. Here, it's not quite so obvious what's happened. But, I mean, one thing I can point out is we've shrunk the area of the circle, right? That's not good. That's not right. And we've somehow kind of rotated it in the wrong way. And the issue here is that, again, we're thinking about things backwards. We're thinking, look, we want to start with this, take our x and our y, apply the transformation to the x and the y, and see what we end up with. But that's backwards. What we actually want to do is we want to plug in a value for x and have done something to it so that we get something right. And so how do we move linear transformations backwards? Instead of going from input to output, we go output to input. We should look at the inverse. And so the right approach is to say, well, what's A inverse? Well, this is nice. It's a 2x2 matrix. This is one of the reasons to work in R2. Besides being easier to graph, inverses are easier to do. A inverse is 1 over AD minus BC times this. And when we work this all out, this is a half minus 1, 1, 0. And so what we want to do is we want, like, our logic was not totally wrong. It just missed this one key point. We want to see, where does this take a generic vector x, y? It takes it to 1/2 x and negative x plus y. And so what we want to do is we want to take our equation and replace x with 1/2 x and replace y with minus x plus y. And then we get the right thing. So this equation is the correct equation for the purple ellipse. So I think this is really nice. I mean, basically what we're saying is that it's the exact same logic as the algebra 2 situation, right? Where all we're trying to do is shift and stretch graphs. We're trying to do more, right? We're trying to rotate, reflect, all that sort of stuff. And the whole idea is that we do this with a linear transformation, but to figure out the correct coordinates or the correct equation to replace x and y with the appropriate thing, we need to use the inverse of the linear transformation for the exact same reason that to move a graph 2 to the right, you do x minus 2. I want to do one more quick example. So let's look at this. This is, depending on the algebra you've taken, you may not have done much with this. This is kind of a crazy looking parabola, right? Usually your parabolas are upward facing, or maybe they're sideways facing. This one is just facing down and to the right. It's doing some sort of crazy thing. I actually wanted to kind of flip this on its head in this example. So in the first example, I was trying to figure out the equation of the crazy parabola. Now I want to tell you the equation and try to figure out the linear transformation. So our standard parabola is y equals x squared. And this crazy looking parabola is 2x plus 3y minus x plus 2y squared equals 0. And I want to figure out what linear transformation is taking our standard parabola and mapping it to this kind of crazy sideways parabola. Right? You can confirm this for yourself. If you type this equation into Desmos or any other graphing software, you'll get this graph. How do we figure out what the linear transformation is? And the idea is going to be similar. Is that we're going to rewrite this thing. I want these to look the same. It's often easier just to put everything on one side of an equation, right? So I'm going to rewrite this as y minus x squared equals 0. And I'm going to notice that we have kind of these two pieces that look similar. And I'm going to try to figure out what is the correct linear transformation. And my first thought is, well, okay, let's figure out. I mean, I'm trying to map these things. I'm trying to think of these things as being mapped to each other. So I want to think about taking y to 2x plus 3y and taking x to x plus 2y. So what matrix is that? Well, if we're going to take x to x plus 2y, that's going to give us 1, 2. And if we're taking y to 2x plus 3y, that's going to give us 2, 3, right? Because if we multiply this out, let's write it like this, we get x plus 2y, 2x plus 3y. So I'm thinking about this, saying, okay, this is maybe approximately the right linear transformation. I mean, in fact, it is. But this is not actually the transformation, right? Because as we discussed previously, this is the wrong transformation to take this to this. I need to look at the inverse. And so actually the transformation I want is the inverse of this. And the inverse of this transformation is minus 3, 2, 2, minus 1. This is what I want. And so what I want to show you here is that if we draw this on the picture, things work pretty nicely. Because I want to see how some vectors get mapped by this transformation. So I'm going to start with this vector over here in red. This red vector is a vector that sits on the original parabola. And I want to see where it gets mapped. This vector gets sent to 2, 0. Right, that's not too hard to work out. I was struggling for some reason. And notice that under this map, so the vector 2, 4 gets sent to 2, 0. And that's this red vector right here. Right, so we're mapping this point on the parabola to this point on the other parabola. And then similarly, if I start with the vector 1, 1, I get minus 1, 1. And that's getting mapped to here. And so this is all a little bit busy, all of these lines on the graph. But the idea is that this linear transformation is mapping all the dotted stuff to all the solid stuff. So you can see that it's actually flipping the orientation, right? So it has a negative determinant. And it's you can kind of see how it's kind of twisting this parabola and turning it. And so the takeaway here is that we can kind of go the opposite direction of what we talked about previously, where if we have an equation, so here I had this equation of this kind of wild looking parabola, I can figure out, oh, this is the matrix of the linear transformation that takes the standard parabola and turns it into this crazy looking parabola. And where we're going with this is that ultimately one of the applications of this is to take kind of crazy looking regions in the plane and figure out their area, or a crazy looking region in 3 space, and figure out its volume by figuring out what linear transformation takes some more standard region and maps it to that region. And so for instance, if we know that something comes from the unit circle, we know the area of the unit circle, and if we know the transformation that sends it there and we understand determinants, we can figure out what is the area or volume in 3 dimensions of this new region.